Most of what we see in our everyday lives is close to stable equilibrium. It's not falling all over the place. It mostly sits still. But nothing is exactly at stable equilibrium. There's always some perturbations or some knocks or kicks that set it a little bit away. And the thing that makes the equilibrium stable is that those little disturbances don't accumulate. The system is forced back towards the point of equilibrium and undergoes a motion called simple harmonic oscillation. From the swaying of skyscrapers, to the ringing of bells, to the swinging of grandfather clocks, to even the vibration of molecules and atoms, so many systems in physics undergo simple harmonic oscillation, it's worth our time to describe the underlying mathematics. The basic system that we'll start with is a mass on a spring. And while this might seem a little bit contrived, we'll see that all simple harmonic oscillations can be reduced to this same situation mathematically. The system is a mass that is supported on a frictionless surface and attached to a fixed point on one or the other sides by a spring with a spring constant K. When the mass is at rest, it will sit at some position, which we'll call x0, and any displacements to the left or the right we'll call x. So we could take the point of equilibrium as the origin of a coordinate system on a one-dimensional x-axis. This system exhibits the behavior of stable equilibrium. If the spring is stretched to the right, a force exists from the spring that pulls it back to the left. And if the spring is compressed, making x negative, then the force will be in the positive direction. Newton's second law then says that this force generates an acceleration. And so we get an essential equation of motion where the acceleration is proportional to the displacement. Actually, there's a minus sign here, which is crucial to this behavior. This minus sign means the force is towards equilibrium and the system is stable. The mass and the spring constant are constants, but the acceleration and the acceleration position, when thought of as functions of time, are derivative related, right? The second derivative of the position versus time function is equal to the acceleration. So this equation, even though it only contains 4 symbols, is not so simple to solve. We can't just plug in, expect to get a value for each of the 4 variables, because a constant value for x would imply a 0 acceleration, and so a constant value can't solve this equation. This is a special kind of equation. You might have encountered these before. It's called the differential equation. And what it is telling us is there's a specific function x of time and a specific function a of time that satisfy this proportionality at the same time as having the correct derivative relationship. So let's see how to solve this kind of equation. Unfortunately, as is the case in most difficult math problems, our best solution, if we don't know anything, is to guess and check. Once we know what some guesses are that work, we can try to generalize. So let's make a simple guess. We know from our experience that a system oscillating around stable equilibrium will generally, go back and forth. Left, right, left, right, left, right. It goes back and forth. So its position, oscillates between positive and negative values back and forth. So a mathematical function that has the same kind of oscillation behavior built into it is a sine or cosine, a sinusoidal function. So let's take a first guess. This is a very crude guess. It doesn't have the right units or anything, but we're just trying to figure out what this kind of equation could mean. So let's guess that the position versus time function is just cosine of t. We could choose sine, not any difference to what works out, but we'll just choose cosine and check. So if we have to check this equation, what does it mean? Well, we could plug in x right there. K and m are constants. We would be given the values of those, or we know them from measurements. But to plug in for a, we have to know the second derivative of x. So let's calculate the second derivative of x. First, we'll calculate the first derivative, the derivative of cosine with respect to t. will be, what is it, negative sine. And the second derivative of x with respect to t will be minus cosine. And this is the acceleration. So now that we've got x and we've got a, these are both functions of time. I don't always write this, but they're all functions of time. If we plug these in, what are we going to get? We're going to get m times negative cosine of t equals negative k times x, which is cosine of t. So this is looking kind of promising. The cosines could be canceled off of each side. The minus signs could be canceled off of each side. But then we would end up with an equation that looks like m equals k. And of course the units aren't right here. Mass and spring constant don't have the same units. And even if we had taken some account of the units, we would still have to ensure for this to be a solution that the mass is equal to the spring constant, which is like, that's kind of bogus, right? There's no reason that those have to be equal. So our guess is close, but it's not good enough. We have to make a better guess. So let's erase this and make another guess. And this time let's try to be a little bit more general. So our oscillation back and forth here, when we guessed cosine, that meant the oscillation was going back and forth between +1 and -1. Well, real oscillations might be of any size. So let's add a quantity called A, which we'll name the amplitude. And this will multiply the cosine function in front. And we'll draw some graphs in a moment to find out exactly what this amplitude really means. And secondly, we know that these oscillations, they may go fast if it's a small system with a stiff spring, or they may be very lackadaisical. They may be very slow, slowly back and forth over a couple of seconds. So to account for that, we'll put in a factor here called omega. Well, the symbol is omega. The name for it is the angular frequency. It looks similar to angular velocity, but it really has a different interpretation here. And this is to account for the fact that the oscillations might go forth at different speeds or different periods. So let's take the second guess and we'll plug it into this equation and see if it works out. First, we have to take the derivatives necessary to be able to plug in for the acceleration. So the first derivative, dx dt, which is, remind us that that's the velocity v. This will be negative a sine omega t. And then something important happens. Because of the chain rule in derivatives, there's a factor of omega that multiplies the whole expression. So negative a sine omega t times omega. Let's go on to the acceleration. Second derivative of position, or first derivative of velocity. If we do this derivative, then we're going to get that minus a, the sine turns back into a cosine. And then we get another factor of omega multiplying the expression because of that chain rule again. So there's our expression for the acceleration a, and let's plug that in. So now we have m times minus a omega squared, I move to the front, cosine omega t. We have to check if that's equal to minus k times the x function itself. So a cosine omega t. All right, and so what we can cancel here, we're in pretty good shape. We can cancel the cosines. All right, and what I want to do is move most of this stuff to one side of the equation. I don't want to cancel too many things because remember, when you divide an equation both sides, you can't divide by 0, right? So cosine is never 0, so that's okay. But this other stuff, I don't know anything about it, so I'll be very careful here. I'll have negative m a omega squared, and then I'll move the ka to this side. So plus ka equals 0. And I can do a bit of factoring here, so I'll write it as a times minus m omega squared plus k equals 0. So if this equation is true, then our guess is a solution to this central equation of simple harmonic oscillations. So how can this be true? Well, there's an easy option, so it's called the trivial solution. If we just let a equal 0, then 0 times anything is 0 and it's solved. Well, what does that mean? It means that our position was just constant at 0. That describes a solution where the mass sits at rest at the origin. So yes, it solves this, everything is 0, but it's not really an oscillating solution, it's called a trivial solution. So let's assume that the a is not 0, and if a is not 0, then that means the omega, the angular frequency, needs to have a specific value to solve this equation. Remember, m and k are constants that depend on how much mass it has and how stiff my spring is. I can't just change those on a whim, but the angular frequency here was just a guess, part of the guess, a generalization of the guess. So in order for this equation to be solved without having to have a equal to 0, we have two options. This angular frequency could be either the positive or negative square root of k over m. So if we square that, then we get k over m here. M's cancel, minus k and plus k gives us 0. So we now call this a solution. So this is the solution. X of t can be equal to a times cosine omega t, where omega is given by the square root of k over m. Notice that I don't really care about this negative solution here because cosine as a function is even. So if I have a minus omega t in there instead of a plus omega t, it makes no difference. All right. So the other parameter in the guess, the amplitude, we find out that that can be anything, and this will still be a solution. Okay, so this is a very simple solution. It's one that works, and it does give us sort of a picture now of how this oscillation would take place. We can have any amplitude. It can go back and forth as far as it wants on either side in this idealized mass on spring system. The angular frequency is determined by the spring and the mass. So a stiffer spring makes the frequency higher, and a larger mass makes the frequency lower. So that fits with our expectations, right? More mass, more inertia, sluggish to move around. On the other hand, stiffer spring, more force, makes it move around quicker. But not in direct proportion, right? There's this weird square root here. So let's try to relate this to some measurable quantities. Remember that for any oscillation, for any thing that happens with an angular frequency of omega, that means that it has an ordinary frequency of omega times, omega over 2 pi. So the way omega appears in this cosine function, that means it's an angular quantity and it's in radians per second. So for the cosine to repeat itself, the argument has to go from 0 to 2 pi, right? So for omega t to go from 0 to 2 pi, that means that we've gone under one entire cycle. So omega over 2 pi will be the frequency for one cycle. So this ordinary frequency really represents so-called oscillations per unit time. So if we have a frequency of 2, there's 2 oscillations per second. All right, the other quantity which is easy to measure is to look at the oscillation and time with a stopwatch or something, how long it takes to complete one oscillation. That's called the period, and that represents really the time per one oscillation. So the period is a proper value measured in seconds, minutes, milliseconds, or something like that, which tells you how long one oscillation takes. If you want to get to that frequency value, then you either invert it to get the ordinary frequency, right? T equals 1 over f, so f equals 1 over t. Or you throw in this factor of 2 pi to get it in an angular quantity with radians per second. So omega equals 2 pi over t. All right, so just to explore this fully then with our solution, the total period of the oscillation would be 2 pi times the inverse of omega, so square root of m over k. All right, so here's a way to predict, how long one oscillation would take if you set up this experiment with a known spring, a known mass. Do your homework to make sure the frictionless surface exists, and this will be a way to predict the period of that oscillation. So it's a way to make clocks, basically. It's a way to set up a specific time value that repeats itself. Again, we see this dependence on mass here in the numerator, so a larger mass takes longer to go back and forth, but not proportionally. And a stiffer spring makes the period shorter. Okay, so now let's explore a little bit more about this value A, the amplitude. First, let's get a handle on it by drawing a graph of this solution. A function, x versus t, we can draw a graph of that. And its cosine multiplied by the quantity A. Cosine function normally goes back and forth, oscillates back and forth between plus or minus 1. So when we multiply it by A, that graph is going to go back and forth between plus and minus A. At a time of t equals 0, the cosine evaluates to 1, and the position is exactly at 1. At a time equal to the period, capital T, then this argument is 2 pi, and the cosine evaluates to 1 again. So back here at a time equal to capital T, we're back at 1. At a time equal to 2t, we're back at 1. And so the motion repeats with a period of t. In between, it goes through these oscillations. So something like, I'm dividing this up into quarters so I can draw it correctly. So there's one oscillation back and forth. Here's the second one. And they would continue on like that basically forever in this idealized system with no friction. It'll just oscillate forever until some other force comes along and changes it. Just to mark out the different locations here, this is one period, capital T. This is half a period when it goes to its negative extreme. And it's at 0 when the time is equal to a quarter of a period. And it's at 0 going the other direction at 3/4 of a period. So the period of an oscillation is naturally divided into 4 segments, and you can think of these as 4 quadrants of the oscillation if you want. Now you might complain when you look at this graph, the oscillation goes back and forth between plus and minus A, so that's okay, but this solution predicts that the oscillation always begins at an amplitude of A, at a position of x equals A at time 0. And so imagine this mass on spring system was set up by one of your lab mates, and you were late to lab, so you just walked into the room and it was already moving, and then you just started your stopwatch at an arbitrary time. You're not guaranteed to start your stopwatch exactly when the oscillation is at a maximum position, right? You can start your stopwatch whenever you want. So this solution appears to not really be able to describe every possibility just yet. It's got a lot of the right features, but it's not fully general. It only can describe situations where the thing is started at a maximum position and let go from rest at time 0. So what we have to do is make a better guess. So x equals a cosine omega t was a solution. It was a good guess, but it was not the most general possible solution. But let's take what we learned from that and make a third guess now. And see if we can hit on this most general possible solution that can describe all situations in this system. All right, so guess 3. Okay, so let's think about this. We saw that adding an amplitude was a good idea. We saw that adding an angular frequency was a good idea. And we saw that having a sinusoidal function was a good idea. So the most general thing we could do that includes all those is to have a term for cosine, which is sinusoidal, and also throw in a term for sine, which is also sinusoidal. Both of these will have the same property, that their derivatives flip into the other function. So they'll still work. So let's go through the check part of our guess. Minus b omega sine. And then here we'll still have plus c. We get an omega from the chain rule. And the sine turns into a cosine. So this is the formula for the velocity in our guess. Here's the acceleration. Now we get omega squared from the chain rule, back to cosine on the first term. Now the minus sign comes out in the second term with sine. We get an omega squared, and we're back to sine. All right, so it's clear again in this scenario, because of our use of sinusoidal functions, that we basically have minus omega squared times the x function again. Look, right? B cosine times minus omega squared. C sine times minus omega squared. So that means we'll get the same formula for omega that we got before. Square root of k over m will be the formula that omega has to satisfy. But what about the b and c constants? What about them? Well, again, since they're just kind of eliminated by replacing this expression for a with x, the b and c constants can be anything, and this will still be a solution. The same as we could have any amplitude and get a solution. But the b and c constants will turn out to mean something a little bit differently. And let's try to discover what that is. So remember our problem with the second guess, the a cosine omega t, was that it didn't seem to match the initial condition, right? It had a fixed initial condition built in of x equals a at time 0. The system could only start at rest from its maximum displacement. So if we want to see what these b and c constants mean in this new guess, we should direct our attention towards the initial conditions. All right, so initial conditions mean the value of x when t equals 0 and the value of v when t equals 0, and maybe the value of a when t equals 0, but we'll start with these two and see what we get. So when t is equal to 0, the cosine evaluates to 1. The sine evaluates to 0. So we get b times 1 plus c times 0. And so at time 0, the x function is equal to just the b constant. For velocity, we're looking at the second line here, right? It was a good thing we did this derivative. So at time 0, the sine evaluates to 0. The cosine evaluates to 1. So we have minus b omega times 0 plus c omega times 1. So the velocity at time t equals 0 is equal to c constant times omega. So what we find out is that these two constants, b and c, are related to our initial conditions. They allow us to have any initial velocity and any initial position. We will say that b is the same thing as the initial position at time 0, and c is the same thing as the initial velocity divided by the angular frequency. So we can have any initial velocity at time 0, any initial position, and that will affect our constants b and c. So here's our most general solution for this simple harmonic oscillator. I'll plug in the physical initial conditions instead of using the b and c constants anymore. We're kind of done with those. We know it's going to be x0 cosine omega t plus, and then the c constant is v0 over omega. So v0 over omega times sine omega t. All right, and I'll put a box around that one. And that is our most general possible solution to this one-dimensional, frictionless, mass-on-spring harmonic oscillator with all the initial conditions included. And omega, of course, has to be equal to square root of k over m to make it all work out. Okay. Now we're going to discuss how this solution is related to our earlier concept of amplitude. We'll find out we need to introduce a new quantity called the phase of the oscillation. Let's first draw a graph that shows sort of what this solution is doing. X versus time. Let's say we have an initial position that's here. This is x0. And we have an initial velocity that is, let's consider a case where the initial velocity is negative. What the heck? So we'll have an initial velocity which is negative. So if v0 is less than 0, what that means for our graph is that it's sloping down, already sloping down at time equals 0. So we're looking at a function that starts at a positive value and sloping down initially. But it's still a portion of this sinusoidal oscillation. So I must be looking at the portion where it's about to go across 0. I must be looking at the portion in sort of the first quadrant of the oscillation, where it was recently at a maximum, we encountered it, we walked in and started our stopwatch when it was a little way closer to 0 and moving back towards 0. But soon it's going to be at 0, and then it's going to continue the oscillation the same as it did before. Right? So something like that. And this same location over here with the same position and the same slope, that will occur at a time equal to 1 period. So that's what these initial conditions x0 and v0 mean. It's like the intercept and the slope at the point of the vertical intercept. What about amplitude? Well, the amplitude we had defined as the maximum and minimum extent of the motion. So between minus a at the bottom, the farthest to the left, and plus a at the top, the farthest to the right. And it's clear from our graph here that amplitude a and initial position x0 are not the same, right? They're not the same. So how can we reconcile these two viewpoints in terms of amplitude and in terms of initial position and initial velocity? What we can do is return to our second guess and modify it slightly by adding a linear angle added into the argument of the cosine. So we still advance through time at the rate omega, radians per second, but now when time is 0, we may start at a different angle throughout the oscillation. So in our first solution, guess 2, this angle was assumed to be 0, and that's why it always started at the top of the oscillation. But if this angle, say, is, if this angle is 90 degrees or pi over 2, then at time 0, this oscillation would begin at this crossing spot here. So let's take this improved guess and compare it to our initial conditions. x0 would be equal to a cosine of phi, since I plug in time as 0, and v0, if we look at, let's see, first we have to do the derivative, right, if we want to discuss the velocity. So let's write that out in all the detail. So we get minus a omega sine omega t plus 5. That's the velocity time function in this model. So the velocity at time 0 would be minus a omega sine phi. All right, so does this make sense? Well, we see the omega showing up in here. That's a good sign. Our guess that we labeled guess 2, where we assumed the phi was 0, would have ended up with an initial velocity of 0, so that would be us starting at rest, and that's what we saw. So what we've gotten by adding in this phase factor here is the ability to start at a different initial position, and to start at a different initial velocity. But how can we choose the right a and right phi to get the right initial position and the right initial velocity? Well, the trick here is that this set of equations here, the x0 and the v0 equation, they're the same equation as like a transformation of polar to rectangular coordinates, right? It's like a radius value, r, times a cosine or a sine of an angle. So we can solve these in a similar way. If we just take this equation here and divide both sides by omega, multiply both sides by -1, right? So we've got a cosine phi is x, and a sine phi is v0 squared over omega. So x0 and minus v0 squared over omega are like the x and y coordinates in this amplitude phase space. Phase is the angle, conventional angle, and a is the distance from the origin. So we can solve for these guys then. We can actually use what's like a Pythagorean theorem, or your identity of trig, cosine squared plus sine squared equals 1. So if we take x0 squared plus v0 squared over omega squared, this will be equal to a squared cosine squared of the phase plus a squared sine squared of the phase. And as we all know, cosine squared plus sine squared is equal to 1. So those eliminate any dependence on the angle, and we could take a square root of both sides and find out how to predict that amplitude from a given initial position and initial velocity. Okay, that's how the math works out. Does it make sense? Well, x0 and v0 are both some value. We could plug those in together to get the amplitude. Yeah, that seems to, I mean, a bigger x0 makes a bigger bigger v0 makes a bigger a. Does it fit with our previous knowledge? If we set up a system that's initially at rest, this v0 term goes away, and we get a equals x0. So yes, it does fit. Right? But it gives us a bigger picture of how the amplitude is influenced by the initial position and the initial velocity. Now we can also get an expression for the phase, which is not as useful. If we divide these two equations by each other, sine over cosine will be equal to minus v0 over omega 0, omega x0, like that. And so we could take the inverse tangent of both sides on this equation to predict the value of the phase. Now the value of the phase is not usually so interesting because it's just shifting the whole graph here left or right by some angle, an angle with respect to the quadrants of the oscillation. So it's not usually very interesting what the phase is, but if you want everything to match up exactly between the x0, v0 description and the amplitude and phase description, then these are the equations which would relate them to each other. Okay, so we've completely solved the situation of this simple harmonic oscillator, a mass on a spring.